Greetings to everyone. My name is Andres Arguello, and I am currently a PhD student at the University of Campinas and a lecturer at the University of Costa Rica. I come here to present to you our work entitled Distribution Network Voltage Controller in Presence of Lost Measurements. This work was conducted in collaboration with my colleague, Dr. Gustavo Valverde Mora from the University of Costa Rica. Here is a quick outline of this presentation. First, I will speak about the motivation that led to this work. Later on, I will describe the model predictive control scheme for distribution network voltage regulation that we used in this project. Then I will detail how to estimate the lost voltage measurements based on available measurements and system characteristics in order to fit the voltage controller with pseudo measurements. And in the last two parts, I will address the test system with simulation results and the conclusions of our work respectively. Distributed generation has gained relevance in the last years, boosted by the rise of new technologies such as power electronics, communication, and computational infrastructures. With more active grids, the necessity to control our assets becomes more important in order to ensure proper power quality and operation of the system. Typical control schemes can have either a central or dispersed controller, and these controls require measurements, especially for the case of centralized controllers taking decisions over a region or a set of assets. However, there is little work in the area of control robust to measurement losses. To address this issue, Professor Gustavo created the research project Control of Electric Grids in Conditions of Restricted Information and Partial Loss of Measurements. So, our interest here is to propose an algorithm to control the voltage magnitudes of the buses in an active distribution network, with medium voltage distributed generation and measurement infrastructure. We intend on using a centralized scheme to coordinate the control actions of all the assets of the grid. However, this controller will also be able to cope with voltage measurement losses. The objective is to secure the monitored voltages within a band with the least control actions as possible. The assets I mentioned previously are the taps of transformers, shunt capacitors, and the reactive power setpoints of the generators. The active power is also considered a control variable, but with a very high cost to its curtailment. Moving on to the second part of the presentation, we will speak about the controller. So the strategy we chose is based on Model Predictive Control, or MPC for short. We obtain a set of optimal corrective actions based on the response of a model of our system. As we can see from the figure on the right, the voltages can be within any of three operating regions, being the normal one, the undesirable one, or the unacceptable one. No corrective action is required unless the voltages exceed the normal operation limits, which allow for a certain hysteresis. This reduces the control efforts. From the figure on the left, we can see we have two horizons. One is for prediction, and one is for control actions. We decided to predict the optimal corrections over a time span of 7 samples. However, only the first control action is applied, and once the measurements arrive the controller in the next time sample, then the calculation is redone all over again. Here we have a summary of the optimization model. The control vector is composed in this work of the set points of the generators, that would be P and Q for the active and reactive powers, and the taps of the main transformer. K denotes the present time sample, and I the future samples of the prediction horizon. The objective function, as mentioned previously, aims to minimize the magnitude and the number of control actions taken to correct the voltages, and it also includes a term of relaxation to guarantee a feasible voltage solution in case of extreme conditions, which is highly penalized. We also define the control changes in this equation over here, relative to the previous sampled value. And we also define the limits of the control variables as well as their limits for rate of change. We also have the voltage limits for every bus and time samples. Finally, the expression to model the voltage of the grid in terms of the previous voltage sample and expected changes applying the control variables is located in the lower part of the screen over here. Now that we defined the control scheme, we can speak about the additional blocks for estimation of lost voltage measurements. The original controller uses P, Q, and V measurements to predict the optimal control actions. However, in case of lost voltage measurements, it excludes such bus from the control buses list. The enhanced version of the controller creates pseudo measurements based on the available measurements and the characteristics of the grid. This allows for improved performance. There are three stages for the estimation process. The first one is the detection of the loss. The second one is a clustering phase to select the most suitable measurements to estimate the lost one. And the third one is the estimation itself. In summary, the pseudo measurements are built based on the last measured sample, that we call Vref, plus a term of voltage evolution, with a delta, as a weighted sum of the evolution of two candidate buses, or available measurements. In order to choose the candidates, we perform a clustering analysis, and this clustering allows for measurement candidates to be in several clusters simultaneously, based on a simple proximity criteria. For example, here we have three axis elements in the right figure, being three lost buses, and we can group several other candidate buses according to that criteria. Notice how V4 and V11 are candidates for both the green and the red clusters. The characteristics that we use for each bus are the voltage sensitivities to the control variables. In this sense, we can define a sensitivity matrix with the same number of rows as the number of measured buses and the same number of columns as the control variables. Such sensitivities are approximated using offline power flows of the system. An example of the magnitude of these three numbers is presented on this table over here. Observe how the bus voltages are more sensitive to certain variables than others. And the criteria we use to do the clustering is the dissimilarity index, which is a measure of how different two buses are to one another. We will have a dissimilarity array which details the distances between any possible pair of buses in the grid. We decided to use the squared weighted Euclidean distance, that would be the SWED, as it gave the best results. The calculation is analog to the Pythagoras theorem, but over higher dimensions. The columns of the matrix are normalized by their variance to avoid one dominating over the others in the final calculation, as for the example of the table below. We can see how the upper line is not normalized and how the lower one is normalized. On the first one, the top of the transformer will dominate over the rest of the variables, and on the second one, this effect is more distributed. The best two candidates will be the most similar to the lost measurement bus. In essence, the two with the lowest dissimilarity. The weights to build the pseudo measurements are based on the inverse of the dissimilarity. This means all of the required information comes from the sensitivity matrix. In the figure on the right, we can see the loss of the red dashed measurement. Note how the reference values and changes are defined with respect to their last available measurement. This avoids accumulating error over time. Once all measurements are available again, the reference is updated. And now we move on to the results. We ran numerous simulations of this 75 buses distribution network on a software named Ramses. This is an electromechanical transient simulation software from the University of Liège in Belgium. the controller was implemented in Fortran. Such system has 8 feeders connected to the transmission grid through a 33 to 11 kilovolts transformer with load tap changer. The grid has 38 loads. The majority of these are modeled as constant currents for the active power and constant impedances for the reactive power. The rest of the loads are modeled as large induction motors. We also modeled 13 3 megavolt ampere hydro generators and 9 DFIGs wind generators of 3 megavolt amperes each as well. All generator models include the capability curves and their respective system constraints. Finally, 71 variables of the system are measured, which are all active power, reactive powers, and voltages of the generators. All voltages at the marked locations as well with the black diamond in the figure, and the voltage at the secondary of the main transformer. All highlighted buses in red will be used for the following examples. And now here we have the performance of the system at two different buses for single losses. The 1145 bus is at the tail end of a feeder, and the 1108 is located at a much stronger point, near the substation. We applied a severe disturbance in the transmission grid at 1 second of simulation. Notice how the controller is able to correct the voltage values and move them to the acceptable bands. Notice how neglecting the control of the lost bus, that would be the blue dotted line, deteriorates the performance of the controller. On the other hand, if the lost measurement is approximated with pseudo measurements of the algorithm, the performance of the controller is practically the same as if all the measurements were available. Moving on, we have the case for multiple simultaneous losses of voltage meters. Notice the controller is able to cope with up to 2 simultaneous losses and still be able to control the voltages as in the original case with full measurements. Observe how reducing the pool of measurements to conduct the estimation deteriorates the performance of the controller as it reduces its visibility. The system does not become unstable as the controller is very robust. However, unnecessary control actions are undertaken if the quality of estimations is left unchecked. To address this last issue, we used a quality limit, also based on dissimilarity as in this expression. All candidate buses to calculate the pseudo measurements are checked, and only those with quality value lesser than the imposed limit are considered. If there are not sufficient candidates, then the bus is taken out of the control pool. We tested several values for the limit and noticed the best one is 0.1, as it is restrictive and does not allow for the remote buses to be taken into account. Nevertheless, the controller is not expected to reach this condition unless a grid scale event occurs. Finally, in conclusion, we presented a centralized distribution network controller robust to lost voltage measurements, which takes the information from the sensitivity voltage matrix of the system as well as the available voltage measurements to estimate the lost ones as pseudo measurements. Such sensitivity matrix was used by the MPC controller as well as for the estimation of pseudo measurements via clustering and dissimilarity techniques. We conducted numerous single loss and multiple loss measurement tests, which confirmed the adequate performance and robustness of the proposed controller. Finally, in case of multiple losses, and to preserve the control performance, we proposed a quality index to avoid poor estimations by evaluating the quality of the candidate buses for approximation. Thank you very much for your attention.